Okay, so in this chapter, we're going to talk about chemical kinetics. And really, when we talk about kinetics, it really does deal with really the rate of a reaction. And when we talk about sort of the rate of reaction, that really does tell us sort of how fast or how slow, for example, a reaction is taking place. We don't talk a lot about it in this class anymore because they kind of took that chapter out, but you will talk about next semester. If you take next semester, I suppose, you'll talk about thermodynamics, and thermodynamics really deals with the idea of whether or not a reaction is going to be sort of spontaneous. And that's sort of a major difference between sort of these two topics. And when we talk about thermodynamics, we talk about reaction. Oftentimes, is it going to be sort of spontaneous? And sometimes people confuse the idea that if a reaction, for example, is spontaneous, that that must mean that it occurs, really quickly or very fast. And that's not necessarily always the case. You can have a spontaneous reaction that takes a very long time to sort of occur. When we talk about sort of it being spontaneous and sort of in thermodynamics, and as you'll talk about next semester as well, um, that's really what you're talking about, is the idea of under these sort of conditions, do you expect a reaction to occur? Has nothing really to do with how fast the reaction may occur or how slow the reaction may occur, but just should that reaction occur. When we talk about sort of how fast, or I guess on the other side of that, how slow a reaction occurs, that's where kinetics basically comes into play. So we use chemical kinetics to basically understand, is this reaction actually going to occur quickly? Is it going to occur sort of slowly? And we could kind of decide those things, based on sort of the kinetics information that we get. So when we talk about sort of how fast or slow a reaction will take place, we're going to really talk a lot about what is referred to sometimes as the reaction rate. And the reaction rate is basically the change in concentration of a reactant or a product over time. And that's what we see here reflected as molarity over seconds. Molarity obviously is a unit of concentration, seconds is a unit of time. So this is kind of the change in the concentration over a period of time, gives us these units of molarity over seconds. Again, letting us know basically how fast or slow something is, either sort of decreasing or increasing, depending on sort of what you're talking about in that particular case. One way we can sort of express that is by what is sometimes referred to as a rate expression. And these look something like this, that the rate is equal to, for example, minus the change in the concentration of A over the change in time. So that delta concentration of A and delta T means the change in the concentration over the change in time. And when we look at a reaction such as this of A going to B, because A is a reactant, we would assume that over a period of time, we should start to see a decrease in the amount of A. Just like over a period of time, we should start to see an increase in the amount of B that's being formed in this particular reaction. And that's actually why we have this negative here. This negative here in this sort of expression indicates that we expect A to be a reactant. We also expect it to be decreasing with time. And I'll explain why that negative there is important in just a second. For our product, we could do the same thing. The rate is equal to change in concentration of B over the change in time. And here we do not have any type of negative. And again, this is because we would expect the concentration of B to be increasing as this reaction takes place. Again, we should be making more products. Thus, the amount of B should actually be increasing. When we calculate something like the rate of a reaction, it is usually a positive number. So this is also why the negative is here for a reactant, because if we take this reaction, for example, A goes to B, and we just have like initial concentrations, we'll say 4 molar, just made up the number, 0 molar. And again, at the end of the reaction, we would expect A to have decreased. So just again making up the number 2 molar, and maybe B got to 3 molar. So how does this affect it? So for example, if we look at the rate, let's just say this was over like 10 seconds or something like this. We could do the rate is equal to minus the change in the concentration of A over the change in time. And if we do that, what we will see is minus change in concentration basically is final minus initial. So our final for A was 2, our initial was 4 molar, and that would be over 10 seconds. And most importantly, when we do this subtraction part here, we get a -2, negative and negative turns our rate for that reaction into a positive number of 0.2 molar seconds. So the rate of this reaction again would end up being a positive number. So when you take that difference for a reactant in terms of its final concentration minus initial concentration, you will always get a negative number because it should be decreasing. And again, that is why we incorporate the negative here in the rate expression for reactants so that we end up with a positive rate. You don't need that if you were looking at something like B, for example. The rate for B would be the rate is equal to the change in concentration of B over the change in time. So just using again the made up numbers here, final would be 3 in the case of B, initial would be 0 molar divided by our 10 seconds. If it was again over that sort of 10-second window, that's going to give us 0.3 molar seconds. So again, we get a positive sort of rate that's occurring here when we look at sort of the product side and stuff like that. So obviously these are some made up numbers, but that again is the purpose of sort of that negative that we have here on our reactant and not necessary here on our product. Again, because reactant will always give us a negative change in concentration, while the products, because they are increasing with time, will give us a positive change. Any questions on that there? So in kinetics, we deal with a lot of graphs. We deal with a lot of sort of visualization of things sort of happening. And we can see here just over a period of time, a couple of ways to illustrate that. Here, the A reactants are these black circles. The products are the red circles. So we can see really at time 0 here when the reaction starts, pretty much we have all reactants that are present, right? Represented by those circles. As time starts ticking away here and going, we start to see some appearance of some products that are occurring. And as this reaction continues kind of all the way through, if you will, we see a much overwhelming amount of products versus our reactants as this guy goes through here. And that is typically what we see here in the graph as well. Again, looking at our initial of A, at time 0, pretty much all our reactant is present. At time 0, we pretty much have no product that's present. And obviously, in order to make the product, we got to use up some A. So we start to see a decrease in A, followed by the sort of similar increase that we see there with B over the period of time. Again, given our rates, and again, that negative here for our reactant, really important as well. Now, visually, we can kind of look at sort of a reaction and sort of visually see what's going on, if you will. In this particular case here, this is a reaction between bromine and some formic acid, making some bromide, some H plus, and CO2. These guys on this side, pretty much colorless over here. And over here is sort of that reddish orangey type color, more of an orangey color, I think. And you can see at the start of the reaction here, we have pretty much reactants, which is basically this guy's color. And as this reaction proceeds, we're making more products, which means we're getting some more colorless things in here. So you can kind of see the color getting lighter until, you know, we can pretty much almost feel like this reaction is over as we end up with this sort of colorless solution at the end. So how can we figure out sort of what is going on, you know, in terms of the concentration or how it's changing? Well, since this solution does have a color, we can use some absorbance values and spectrophotometry to do that using something like Beer's law. Talked a little bit about, I think, in an experiment. A is equal to, say, BC. That's absorbance. Beer's constant. And that is concentration. And basically, we could do this because light of a specific wavelength will be absorbed by the sample and not reach the detector. And if you remember, I think it was the Kool-Aid experiment, right? We tested the sample at a bunch of different sort of wavelengths until we look for that sort of maximum absorbance, right? And that maximum absorbance is where we want to set our spectrophotometer to take these readings. And that's because that will give us pretty much all of this area here underneath the hill to take absorbance values. A reminder that, if you decided, well, I want to set it more at 600, that's pretty much all you're going to get in terms of absorbance values, not very many. And you're not going to have very many samples that are going to be pretty much on scale. Now, how is this helpful? It's helpful because, as we talked about before, the absorbance value is proportional to the concentration of whatever is making sort of the solution have a color. In this case, it would be BR2. So the more color that we see in terms of the BR2 being present, the more absorbance values we will have. So at this point, we'd have a pretty good absorbance value for the bromine, which would mean we'd have a pretty good concentration for bromine. As we would get down to here, we would start to see the absorbance values get lower, again, because there's less BR2 present and obviously more of our sort of colorless products as it goes through this. So again, a reminder, we shoot the light, it gets absorbed by the sample, again, based on sort of the color that we see. Now, forgot what I was going to say. That's bad. Maybe it'll come to me. We'll see. When we're using this sort of Beer's law and we're setting sort of the wavelength theory, as it came to me, remember that, there is a difference in terms of the color that we actually see, like in the beaker of the solution, and the color that's being absorbed. So remember that we actually see the complementary color to what is being absorbed. So, for example, again, this solution, which is kind of an orangey red color, again, you might think, well, I should set it to my orange red sort of absorbance or wavelength. And you would actually, again, set it to the complementary color to orange or red. And that's what you would actually, where the wavelength would actually be absorbing. So another couple of ways we could kind of represent some of these things are this reaction. For example, if we took some data for this reaction of the BR2, we can see over time we do see basically our decrease with the concentration of BR2 over time. And we could talk about kind of two sort of rates. One is sort of an average rate, and one is sort of an instantaneous rate. You kind of pick an instantaneous rate for a specific period of time. You could do that by taking the slope of the tangent of this line for some points. And we do see that the rate, it does vary a little bit here if you just kind of look at a specific window. Or you could take sort of the average rate, which is sort of over the entire sort of experiment or run, what is the rate that's happening in that particular guy. And in the case of BR2, it'd be the change in the concentration of BR2 over change of time. Again, we have our negative here because when we do this subtraction, this is going to give us a negative number. And that negative is going to turn our average rate into a positive number. So what is the difference between those? Well, for example, if you're driving your car, and say you're driving from here to say Arizona or something like that, maybe along the way you're doing 65, 70, 75, 80, 85, not 90, I hope, right, or anything like that. But there may be instances along your route there that maybe you're going a little bit faster, maybe you're going a little bit slower. And if you just take that sort of window of time, you may see yourself sort of driving at whatever, we'll call it 85 miles an hour. Still about 10 miles over the speed limit there if you're in Arizona, but about 85 miles an hour for that one little period of window, which hopefully there's no police officers or anybody behind you while you're doing that. But if you average it out from, say, your trip from California all the way to Arizona, perhaps maybe you only did drive on average for the whole trip, maybe about 72 miles an hour and stuff like that. So, the instantaneous rate is sort of a sort of specific window shot of how fast the reaction is going. And again, it's much like driving. There might be points along the road there, or the reaction, where sort of faster areas, and there could be some slower areas in the reaction that sort of occurs. But if you average it as a whole, you get this sort of average picture for how fast this particular reaction is sort of occurring. We'll talk maybe a little bit about that towards the end of the chapter, that not all reactions occur in sort of a one-step fashion. What I mean by that is not all reactions go directly from reactants to products. It may actually occur in several steps, and some of those steps along the way may be slow steps. Some of the steps along the way may be faster steps. And again, that's where you get those sort of differences and sort of those instantaneous rates, by looking at sort of a window of time versus looking at the entire reaction as a whole. Looking at this reaction, and again, some of the data here, we can really create a relationship that gives us a constant sort of value. So again, if we look at sort of the initial rates here, for different sort of periods of times, we do see a lot of variations in terms of how fast that reaction is sort of taking place. We could kind of normalize it and get almost a constant value all the way through by looking at something which is referred to as the rate constant, which is what the little k is. And we get that from what is referred to as a rate law, like this guy right here. This is basically a rate law. Rearranging that rate law, we solve for little k, which is known as the rate constant. And little k is the rate constant. Kind of tells you, for instance, sort of how fast the reaction is taking place. And that's not to be confused with, if you take the next class there and part B, pretty much all you'll talk about for the majority of it is, for exaggeration purposes, large K or capital K, and that's the equilibrium constant. And that is something a little bit different. So in this chapter, we're not going to talk about this guy. We're talking about the little k. Little k is important. We do get sort of a relationship. We look at the rate versus bromine concentration here. We do see that as the concentration of bromine gets larger or started larger, the rate at which it's reacting is much higher because there's a lot more of it there. As the concentration of bromine starts to decrease as the reaction goes on, we see at different points the rate of it also starts to decrease as well, in sort of this linear fashion. The rate constant is a constant value for a particular reaction the way it's written at a specific temperature. And it also gives you some really important pieces of information in terms of what type of reaction you're dealing with. For example, when you look at the units here for the rate constant, which in this case are reciprocal seconds, that is the units that we associate with what is referred to as a first order reaction. And we'll talk more about that later on in this sort of chapter. But the rate constant, in addition to sort of telling you how fast or slow a sort of a reaction is taking place, it also could give you pretty good information in terms of what type of reaction or how that reaction is actually taking place. Now, not all the time do we always have, say, a solution that has some type of color to it, which would allow us to do some spectrophotometry, follow the absorbance value. So perhaps if we did a reaction like this, where there's really no color sort of happening here, And because there's no color to the solution, even though it looks yellow in there, there's no real color or anything like that happening. It makes it very hard to sort of obviously follow the absorbance value because technically speaking, your solution will look basically zero absorbance all the way through because there's nothing for the light to absorb as it goes through. So in this particular case, though, we are producing a gas, and a gas would usually involve some type of pressure being developed. So since the O2 in this reaction is the only gas that's present, um, as soon as we start to see some gas happening, we know that obviously this reaction is going towards our product side and gas is being formed and we're actually making products. So we actually can use something like our good friend PV equals nRT here, and we can actually do a rearrangement like we talked about in the gas chapter, where we solve for N over V would be P over RT. N in the ideal gas law is moles, and V is volume in liters, and that means that is moles per liter, which is the molarity. So we essentially can follow the molarity of this gas by actually following the pressure. If you did this experiment, temperature would probably be constant. R is the gas constant. So really we could just look at the change in the concentration or the change in the pressure over time, and we would be able to really follow, what is happening. So when we just go N over here, I got a little moved around there, gives us our concentration of our O2 over times RT. Rearranging gives us 1 over RT times the pressure. Sorry, got a little all messed up here. And again, what this basically allows you to do is just to follow the pressure over a period of time. And you can incorporate that with your time element. And now you could have a change in the concentration change in pressure over time. And that would also relate to how the process or the molarity there of the O2 is changing with time. So even though we may not have something that we could take advantage of absorbance values with, because there's really no sort of way to absorb anything because everything's colorless, we can then sort of take advantage of pressure and follow the pressure and do some calculations to relate it to how the concentration is changing with time. Any questions on that there? All right, so it is chemistry, so it does need to involve some stoichiometry. So obviously, when we're dealing with reactions, we do need to deal with sort of the stoichiometry that's involved as well. And we can write again what is referred to as a rate expression, which is these guys. And to write a rate expression that really does take into account the stoichiometry, the mole to mole relationship. So in this particular guy here, it's a 2 mole to 1 mole relationship in terms of the moles there. We could write for A that the rate is equal to, and again, that's a minus there, 1 over 2 change the concentration of A over change in time, while the rate of our product would be change of B over the change in time. Again, no negative here, but negative over here. The 1 over 2 comes from the actual coefficient. By doing 1 over the coefficient, we're able to kind of in one calculation take care of the stoichiometry or the mole to mole relationship for everybody. On the right hand side, it's really 1 is the coefficient, and that's why we don't have any numbers here, because it's essentially 1 divided by 1, which is 1 basically. So that's why we have no 1 over the coefficient, because it technically does equal 1. So in general, you can write a rate expression for a balanced reaction like so. The rate is equal to minus 1 over A, change the concentration of A over change in time, equals 1 over B, change in B over change in time, 1 over C, change in C over time, 1 over D, change in D over time. And again, we see our negatives for our reactants, no negatives here for our products. And this is a really nice relationship because essentially you just need to know one piece of information. So you need to know maybe how a reactant is changing with time. You need to know how a product is changing with time. You even just need to know maybe the rate, and you can pretty much figure out how everybody in this reaction is going to be changing with time. You could write them all as one equal to each other. You could just break out the ones that maybe you are interested in, like -1 over A, change in concentration of A over change in time, or the rate of, say, 1 over C, change in concentration of C over change in time. You could do them separately, but this rate and this rate will be the same. And that's sort of what sort of ties them together. That's basically the average rate for a particular reaction. And that's why if you just know one piece of information, you really can sort of figure out how everybody else is changing. I think we talked about it before, but just to remind everybody, when we do this bracket, that does mean concentration, and usually means molarity, which is moles per liter. So let's take a look at one here. Why don't you write the rate expression for this, guys? See what you come up with. Okay, so let's take a look at this one. So we could write the rate expression. Again, we could just do it for the whole one if you want. You could do it individually. We could say the rate is equal to minus the change in the concentration of CH4 over the change in time. Here, the coefficient for CH4 is 1, so it's basically 1 over 1, which is why there's no sort of numbers there. It's basically 1. But we do have the negative here, which is important because it's a reactant. That would equal minus, again, because O2 is a reactant, 1 over the coefficient, which is 2, change in the concentration of O2 over the change in time. That would equal, now we're going to our product size, so again, we should be expecting it to be increasing with time. This would be the change in the concentration of CO2 over the change in time. Here again, it is 1 over 1, so that's why there's really no numbers kind of put in there. It's a coefficient here is 1, and that would equal, again, our water, which is also a product, so it should be increasing with time, 1 over the coefficient of 2, change in the concentration of H2O over the change in time. So again, they're all basically equal to the same, and this is really the average rate for the particular reaction, which again should be a positive number. So, if you were told how, one piece of reactant or product sort of changing with time, you can basically plug the numbers in and sort of see how everybody else is changing. You can see how the average rate of that reaction would be in that particular case. Any questions on that there? So why don't we try one with some numbers? So why don't you give this a go? So in this particular reaction, the I minus concentration changes from 1 molar to 0.868 molar in the first 10 seconds. Calculate the average rate in the first 10 seconds and the change. This is a typo there, should be change in time. So we're basically looking for the change in the concentration of H plus over the change in time. So that's sort of what we're looking for there, and the average rate. So why don't you take a couple minutes, see what you come up with. Again, use the rate expression and see if you could sort of figure it out, and then we'll talk about it. Basically, the I minus changes from 1 to 0.868 in 10 seconds. We want the H plus concentration. So really, you could write the rate expression for those two things that you're sort of interested in. Clearly, one thing that you're interested in is the I minus. So just looking at the reaction, we know that the rate is equal to minus 1 over 3. Again, the 3 because of the coefficient, the minus because it's a reactant, the change in the concentration of I minus over the change in time. The other guy that we're interested in is obviously H plus, which we can do the same thing for H plus, and we could say that the rate is equal to also going to be negative because this is again a reactant, should be decreasing with time, 1 over the coefficient, which is 1 over 2 there, and that's going to be the change in the concentration of H plus over the change in time. Any questions first off on those two things? So really the information that we have kind of to work with is the I minus, right? And basically the change in concentration means final concentration minus initial concentration. So if we put that into our rate expression here for the I minus, the rate would equal 1 minus 1 over 3. Now our final concentration of I minus, the important is it's actually going to be this. So it's a reactant. It's going to be decreasing with time. So it is 0.868 minus 1 molar, which was our initial. Now, you may be saying to yourself, does it matter to do it that way? And the answer is it does actually matter. And I'll show you here why it does in 1 second. But over our time, final time would be 10 seconds, initial would be 0. We could probably safely assume. The reason, again, it's important to make sure you do final minus initial here is when we do the 0.868 part minus 1, that is going to give us a negative number here when we subtract those two. And that then divided by 10, also divided by 3, gives us a negative and a negative number, which then turns us into a positive number for our rate. So remember that this guy does need to be positive. So just simply taking the difference there and not really doing final minus initial, you may still end up with a negative, which technically would be incorrect for the rate. Also, there are some units that are here. Molarity is up on top, seconds is on the bottom, so nothing has really changed or canceled, and it would be 0.0044 molar seconds. Any questions first off on that part of the calculation? So why is that number helpful to us? Because we are looking for this part right here, the change in the concentration of H plus over the change in time. And what we just solved for right there, which is this number, is the rate. And that rate is the same rate as here. So we actually have that rate right now. And that's going to help us get to the second part of the question, which was what is the change in concentration of H plus over the change in time? So now focusing in on the H plus relationship, 1 over 2 change in concentration of H plus over the change in time. Putting in our numbers, 0.0044 molar seconds is equal to minus 1 over 2 change in the concentration of H plus over the change in time. Remember, again, we are interested in this guy right here. That means to get it by itself, we actually need to multiply by 2, which is a very common error people make. They divide when they should multiply, multiply when they should divide. So again, thinking mathematically to get that 2 to the other side, you need to multiply. Also really important is you're not just going to be multiplying by 2, but there is a negative there as well. So you're going to be multiplying by negative 2, which will give us minus 0.0088 molar seconds is how the change of H plus is over the change in time. Question on that one there. Now, we do see a negative here, and that is okay because we are specifically talking about how the H plus concentration is changing with time, not the overall reaction, but specifically that reactant changing with time. And it's negative because it's a reactant, so we know that it should be decreasing with time. So the negative there is actually needed to indicate that that guy is decreasing with time. Any questions on that there? Now we just saw one here. Let's try this one here and see what you come up with. If we have 2.4 times 10 to the 2 grams of NOBr, molar mass from the periodic table given to you, 109.91 grams per mole. We'll make it official there. Decomposes in a 200 milliliter flask in 5 minutes. Find the average rate of Br2 production in molarity per second, given that reaction that's there. So take a couple minutes, see what you come up with, and we'll talk about it. And we're interested in Br2. So again, that's kind of a good place to start with. Scribble all over the page. But we can start with the rate expression for each of those. So based on the equation there, a reaction, the rate of the NOBr would be minus, because it's a reactant, 1 over 2, which is the coefficient. The change in the concentration of NOBr over the change in time. We eventually want to get over to BR2, which is on the product side, and we could have an expression that the rate is equal to, again, it would be positive because it's a product. Also, the coefficient is 1, so it's 1 over 1, which is 1. The change in the concentration of BR2 over the change in time. So really there is a couple of different ways you could approach this problem. You can approach it like a regular stoichiometry problem, but we'll do it kind of like what we've been doing before. We have the NOBR here, grams. We also have the molar mass. So from these two pieces of information, we could get the moles. We know the volume here, which we could get liters. Moles divided by liters is molarity. So we could really get how the NOBR concentration is changing over that 5 minutes. So that's where we're going to start. We're going to take the NOBR information, which is 2.4 times 10 to the 2 grams NOBR. They were nice enough to give us the molar mass from the periodic table, which is 109.91 grams per mole. That's going to get us 2.4 to the 2 divided by 109.91. Gets us 2.18 moles of NOBR. We can convert that's basically 200 milliliters into 0.2 liters by dividing by 1,000. That will then get us the molarity of the NOBR that's basically decomposing, or the concentration of it. So if we divide it by 0.2 liters, that gives us a 10.92, we'll call it, molar there. First off, any questions on that part of it? Now, I'm going to make this negative 10.92 molar. You might be wondering, why am I making it negative? I'm making it negative because in this case, even though it didn't really tell us it's negative, remember that this number right here basically came from the concentration of NOBR final minus the initial. And since the final will always be lower concentration than the initial, technically when we do this, remember, we should get a negative number for our reactant. And that's why we would put the negative here, again, because later on we're going to have an extra negative that we need to deal with. So you can either do it right now, you could wait for a second and do it at that point. But at some point, you got to take that negative into account here so that you don't get the wrong sign. That's just the molarity part. Remember, when we talk about a rate, it is molarity per second in this case, since that ultimately is what we're looking for. The time that was given to us, though, is in minutes. So you also need to do a little conversion here of minutes to seconds, so everybody's in the right units. We go with 60 seconds, I hope, in a minute. That's going to be 300 seconds. So now I have the molarity, I have the seconds. I now have what I need to put into my rate expression here. So the rate is going to equal minus 1 over 2. My change in concentration of NOBR was minus 10.92 molar, as it's decreasing with time. And the time basically is like 300 minus 0, basically, so 300 seconds. Putting all that in there, we end up with 10.92 divided by 300, also divided by 2. Looks like a 0.0182 molar seconds is the average rate. And again, in terms of that negative that I just did a second ago, it's because of this negative here. Remember, this guy needs to be positive, so that's why we did need to insert the negative here, so that we end up with sort of the correct sign. Any questions on that so far? Now, this is really all doing with NOBR, but we're interested in the BR2. So if we rewrite that expression for the BR2, the rate is equal to the change in the concentration of BR2 over the change in time. We essentially want to solve for this, and that equals the rate. So where did we find the rate? Right there, which is this number, which means this guy equals this number here. for our BR2. And that also does make sense because, again, BR2 is a product, so it should be increasing with time. And here we do see a positive number. And again, that's why you got to be kind of careful with the signs along the way here so that you don't mess up anything. Any questions on that calculation there? Now, I mentioned earlier that, you could technically do this a different way. When we do the 1 over the coefficient, it takes care of the stoichiometry part for you, the mole-to-mole relationship. If you want to approach these problems more as a sort of stoichiometry problem and then kind of incorporate the rate aspect of it, you could do that as well. So what that means is, for example, if I just picked up with my 2.18 moles of NOBr, and I want to do my mole to mole relationship between these two guys, we could have done that right off the bat if you wanted to. And we see that there are 2 moles of NOBr and 1 mole of Br2. And if we did that, that would give us 2.18 divided by 2. That's going to give us 1.09 moles of Br2, which we then could have divided by our volume and turned it into molarity. And if we did that, we would get 5.45 molar for our molarity there. And at this point, we then could divide it by our 300, which is our seconds. At this point, divide it by our 300 seconds. And lo and behold, we end up with 0.0182 molar seconds. So you could do sort of the stoichiometry part and then kind of take it over there. Yeah, so again, to answer your question in terms of how did I get this guy to be negative, I got the guy to be negative because I know that it's a reactant, which means when we sort of do this part of it, right, which is right here, this is the change in the concentration of our reactant. It's a reactant, so it should be decreasing with time, which means when we do our final minus initial, like over here, it should always end up being a negative number. And again, it may not seem that important to put the negative there, but again, it's important because if you did not put the negative there, you would end up with a negative rate, which would then give you a negative guy for this bottom one, which should be positive. So it's a slight little thing you just got to kind of watch out for in terms of the signs. But even though they didn't explicitly sort of tell you that it's going to be negative, you have to understand that it's a reactant, so it is going to be decreasing with time. Other questions on that? Now, again, you can see here we basically did our sort of stoichiometry, straight sort of stoichiometry problem. And to be honest with you, it is the exact same thing as why we do the 1 over 2 is for the stoichiometry part, because if you look at the stoichiometry part, we did 1 over 2. Yeah. So this way on the left, like we've been doing, sort of wraps the stoichiometry part all together in sort of the calculation, which maybe is less room for error. But if you want to kind of do it more just a straight stoichiometry problem first, you're really just doing the same math. But it's your call in terms of that. Any questions on that there? Our rate expressions. So these again are rate expressions, which again allows you to really determine how everybody in the reaction is changing. You can figure out how reactants are changing over time, figure out how products are changing over time, figure out the overall average rate of how everybody's sort of changing over a period of time. And the nice thing about it is you really just need one sort of piece of information like we had here. We had enough information about NOBr, and that allowed us, if we wanted to, we could go through and figure out how NO is changing. We could pretty much figure out how everybody else is changing as well. Any questions on these rate expressions here? Oops. So that was the one we just did. So let's talk about then some of these factors that do affect the reaction rate. And we're going to talk about some of these guys as we kind of go through the rest of this chapter. But the nature of the reactants are important, sort of the physical conditions they're in. So if we have smaller molecules, because they're smaller, they're able to sort of react faster. They're probably moving around a lot faster as well. That's going to help the rate of the reaction. Typically, gases react faster than liquids, which react faster than solids. Again, gases, just by that nature, they're flying around. They have a lot of energy, which means they're kind of good to go in terms of reactants. They're pretty good to sort of start the reaction occurring. Liquids as well, still a lot more movement than you do in solid. Solid, everybody's sort of locked in, very rigid, right? Things don't have a lot of energy. Things aren't moving a lot. It's going to be much slower to react. But when we do have solids, depending on the type of solid, it's sort of important as well. If you have more of a powdered solid where it's sort of spread out all over, it gives a lot more sort of surface area for things to sort of react with it and sort of interact with sort of the solid, as opposed to sort of a block solid where there's just a small amount that's sort of exposed. Sort of spreading out does that, increases the reaction. Certain types of chemicals are more reactive than others. Things like the activity series of metals, so those single replacement reactions we talked about. There are certain metals, right, that will replace other metals. Some metals will not replace other metals. So that's important. And ions, kind of like gases, they're sort of good to go as well because they're pretty much no bonds there that needs to be broken or anything like that. They're floating around in the solution, which means they just need to find somebody and they can start sort of the reaction to take place. Other things that sort of affect the reaction, one really big sort of effect on reaction rate is the temperature. So when we add temperature, or increase temperature, I guess a better way of saying that, we're really adding more energy, right? When we add more energy, everybody has more energy, allows things to start happening in terms of the reaction and stuff like that. Vice versa as well. If you kind of lower the temperature, everybody loses a lot of energy. They have less energy, which means the reaction is going to take a little bit longer for it to sort of take place. So it's just a general rule is typically if you increase the temperature reaction by about 10 degrees Celsius, you typically will sort of double the rate of the reaction in a lot of cases. Um, Not all cases, but it will a lot of times increase the rate of reaction. We'll see sort of that relationship later on in this chapter, some referred to as the Arrhenius equation. It basically deals with the rate and temperature changes that occur. Another important way that you could kind of speed up a reaction is by adding a catalyst. A catalyst is not a reactant and it's not a product. So when we deal with a catalyst, not a reactant, it's not a product, and it doesn't get used up. You could kind of think about a catalyst as something that is there to sort of facilitate the reaction occurring more efficiently, I guess is one way to put it. So without the catalyst, maybe you got things flying around and they got to kind of find each other. Maybe you put a catalyst in there, those guys are attracted to sort of a central location. And because they're attracted to a central location, they're going to come in contact with each other a lot quicker. Sometimes they may even help create the right environment for the reaction to take place as well. Most of the time when we do talk about catalysts, most of the time people talk about it in the aspect of it speeding up a chemical reaction. Probably 99 times out of 100, if somebody's talking about a catalyst, that's usually what they're talking about. There are certain catalysts that can kind of slow down a reaction, and those are sometimes referred to as a negative catalyst. As we'll talk about towards the end of the chapter, catalysts can be homogeneous, which means just like homogeneous mixtures, they're in the same phase as the reactants. Or they could be heterogeneous, like a heterogeneous mixture. You see different phases, different layers. They will be in different phases than the reactants. Um, and again, this could be something like a metal, like platinum or something like that. And a lot of times you do see catalyst written on top of the arrow, like maybe use a platinum, maybe H plus, which implies some type of acid is being used as a catalyst. So sometimes, it could just create the right environment for that reaction to sort of take place a lot easier. Concentration is also another big thing in terms of how fast a reaction takes place. In general, the larger the concentration of the reactants, the faster the reaction would take place, which means if you think about molarity's true whole definition, it is moles of solute over liters of solution. And for the most part, it is the solute that interacts and reacts, which means if you have a large concentration, then you probably have a big amount of solute floating around in that solution, which again just comes to the idea of they don't have to wait a long time to find somebody to sort of react with. You have a pretty good concentration that occurs. It increases obviously the frequency of those reactant molecules coming together. When we talk about concentration of gases, it depends on the partial pressures of the gas. Higher pressures, higher concentration. What else goes with gases and high pressures? Usually high pressures are small volumes, right? Which means our gas molecules are now shoved together under those conditions and obviously are going to come in contact with each other a lot easier. So it would allow that reaction to really occur a lot faster. Any questions on that there? So what we're going to talk about now, though, is what is referred to as the rate law. And the rate law is a little bit different than the rate expression. It actually deals with just the reactant. So the rate expression, like we were dealing with before, dealt with both the reactants and the products. Rate laws deal with just reactants. So nothing about the products in our rate law. It's just about the reactants. They're important for how the reaction takes place. And this is what sort of a generic rate law looks like. It is the rate is equal to K, which is our rate constant, times the concentration of A and B, these are concentrations, to the respective orders. So X and Y are the orders. X and Y are not the coefficients in the balanced equation. So X and Y, not the coefficients. In fact, rate laws and these orders are always found experimentally. So these are always found experimentally, which usually means that you will be given a table of information like you did a reaction or an experiment or several experiments, and you need to use that information to figure these things out. You can actually figure out the overall order of the reaction by adding those together, like X and Y. If you had X, Y, and Z, if you had three of them, you add them together. Now, the rate law, again, tells us certain things. It tells us, what's going on in the reaction, the orders. You could kind of think about it as sort of the proportion of that reactant that you need to keep and maintain a rate. So for example, let's just say hypothetically we had a rate law where the rate is equal to K times A, we'll say to the first power, and B to the second power in this sort of hypothetical situation. And let's just say that, we have concentrations of A in, say, one experiment we were doing where we had the concentration of A was 2 molar, the concentration of B was 2 molar. So if we plug this into sort of this expression here, we will end up with the rate for this reaction is going to be, we'll take out K because it's a constant, so not that important right now, but basically 2 times 2 to the first order, which would be 2, times 2 squared, which would be 4. 4 times 2 is 8. So the rate here would be something like 8 molar seconds or something like that, hypothetically speaking. Now, what happens in this guy is we go, well, you know what? I want to increase the rate of this reaction, right? How can I do that? How can I make this reaction occur faster? Well, what happens if I increase the concentration of B? So let's just say in this experiment, we started with 2 of A, but we increased the concentration of B to 4 molar to begin with. Doing our same math, it would be putting the 2 in for A would be 2 to the first power, which is 2, putting it into B, 4 squared would be 16. 16 times 2 is 32. I know it says 22 when we write 32. 32 molar seconds. So what did we just see here? By increasing the concentration of B by doubling it, because the order of B was second order, it actually did what to our concentrate our rate? Our rate actually went up by a factor of 4 in this case. So we could see, we could use these things to help us understand, maybe in a situation we need to make the rate or the reaction occur faster, we could do that. Maybe in a situation we don't want to sort of make it faster, maybe we want to make it, kind of slower, we can maybe change A a little bit or decrease B concentration, and we could use this to sort of figure out how fast or slow a reaction will occur. And we can kind of play with it by knowing the orders of those guys that, what will have the bigger effect on it. For example, what would have the bigger effect if I did a third experiment here and I decided, well, I want to increase A's concentration to 4 molar, but keep B's at 2 molar. So again, if I put that in there, 4 to the first power would be 4. 2 times 2 is 4, and that would give me a rate of 16 molar seconds. So in this case, what we see is by increasing A, doubling A, it will double the rate of the reaction. That's different than doubling B in this example. It actually made the reaction occur 4 times faster. So, you can use these orders, and what these orders sort of mean is basically sort of the proportion that you need of these guys to allow a reaction rate to occur at a specific sort of time or way. And you could also use it and manipulate maybe the concentrations. For example, in a practical sort of application, maybe you set up a reaction or an experiment where you're trying to measure, absorbance values over a period of time, but the reaction happens so quickly, by the time you get it all in there into the machine, the reaction's over. So you would need to slow down that reaction so that you could play with those sort of concentrations to help you do that. So that's sort of a practical application of understanding the rate law and sort of the orders that go with it. Any questions on that? Okay, so what does a typical sort of problem look like? Well, it looks like this. You're oftentimes given a table like this for this particular reaction. So we're going to go through this together. I'm going to kind of show you how to work one of these type of problems. But the goal here is to figure out the completed rate law. And that's with the orders. We could also figure out the overall order of the reaction. And lastly, we'll figure out what is the value of the rate constant. So these are the 3 things that are typically asked of you when you get a table like this in this type of problem. So we're going to start with the first one, which is we're going to try to figure out the completed rate law with the orders. And by the way, you really can't figure out the other 2 until you kind of do that part of it. So we'll start with the generic sort of rate law for this guy, which is the rate is equal to K times the concentration of F2 to the X. And again, you can use any letter you want. I'm going to use X and Y. And ClO2 to the Y. Again, here, we're just doing our reactants. So when we look at a table like this, and this is a typical table that's given to you, what you want to do is really compare kind of 2 experiments. So we have 3 experiments that were done, experiment 1, experiment 2, experiment 3, with some different concentrations of our reactants and some initial rates that occur based on what we started with. So there's a couple different ways you could do this, but most people, you need to do sort of like a mathematical approach, and that's usually the best way to do it. So mathematically, you could kind of use this equation that you sometimes see, which is the rate 2 over the rate 1 is equal to K to the A to the X and B to the Y divided by KA to the X and B to the Y. Now you may be asking, do I just go to the table then and grab the first and second entry? And that's not really what it means. It means that you should go to this table. And in this particular table, there's just 3 entries, but you may have a table that has 4, 5, 6, a whole bunch of entries. but you usually will have a table that has at least 3 entries in most cases. But what you want to do when you go to this table is it's pretty much math, which means we don't want a bunch of unknowns, right? So we want to kind of minimize the number of unknowns we have. And when we do that is we want to go to the table and find 2 entries where one of the concentrations remains constant and one concentration varies. So we're looking for 2 entries from the table where one concentration of one of the reactants stays the same and the other one basically varies. So if we look at this table, we can see that F2, for example, remains the same concentration in experiments 1 and 2, but the concentration of the other reactant does vary. So we're going to use those two to help us figure out the ClO2's order. So using experiments 1 and 2, the other thing that's sometimes helpful, and you don't have to do this, but sometimes it's helpful because you sometimes will come up with kind of whole numbers at the end, is to pick the one that has the larger rate and put it on top. So in comparison of 4.8 to 1.2, 4.8 is the larger number, which means for me, I'm going to put everybody from entry number 2 up on top. That means that the rate for entry number 2 would be 4.8 times 10 to the minus 3 molar seconds equals K, which I do not know. For entry number 2, the concentration of F2 is 0.1 to the X. Concentration of ClO2 is 0.04 to the Y. So everything that I just put here came from entry number 2, basically. So everything here came all the way from entry number 2. Now what I'm going to do is basically put everything from entry number 1 on the bottom, 1.2 times 10 to the minus 3. Again, K. And for entry number 1, 0.1 to the X and 0.01 to the Y. Everybody on the bottom came from entry number 1. Any questions on that? At this point, it is math time. So when I take 4.8 times 10 to the minus 3 and divide it by 1.2 times 10 to the minus 3, I get a 4. That's a lot of math there. Now, when we come to the other side, K on top and K on the bottom, those are the rate constants. And because they are the rate constants, they should be a constant number. I don't know what it is at this point, but I do know on top and bottom, they should be the same. When I come to the 0.1 to the X and the 0.1 to the X, I don't know what the order is for this guy yet, but I do know that they should be the same number, which means this guy and this guy are going to cancel out. When I do my next guy, the 0.04 divided by 0.01, I also get a 4 to the Y in this case. Any questions on that there? You could probably visually see it that in this case, Y is equal to 1. If you're not sure, you could also take the natural log of both sides. When you do that, the Y will come down, and you basically dividing the natural log of 4 divided by the natural log of 4. It won't let me right there. We'll come up here. Basically, natural log of 4 divided by natural log of 4 would equal Y, basically, which should equal 1. So if you need to, you can't visually see what it is. You can basically take the natural log of both sides and divide. That's why sometimes putting the larger value up on top is helpful because it usually will give you, not 100% of the time, but a lot of times it'll give you more of a whole number, which will make it a little bit easier to see. Any questions on that so far? Now that I figured out the order for Y, what I want to do now is go back to the table, and I want to keep the ClO2 constant, which looks like experiments 1 and 3 will do that, while having our F2 vary, which looks like 1 and 3 will also do that for us. And again, we're going to now look at experiments 1 and 3 in this case. Again, I'm going to put the larger rate on top, which looks like experiment 3 in this case. So experiment 3 is going to go all the way across the top. And that's going to give me 0.2 to the x, 0.01 to the y. And now I'm going to put everything from entry number 1 across the bottom. 1.2 times 10 to the minus 3, k, 0.1 to the x, and 0.01 to the y. Now doing my math, that is going to give me a 2 is equal to, again, the k and the k will cancel. In this case, 0.2 divided by 0.1 gives me 2 to the x. And again, we held this guy constant, so he will cancel out. Again, you can probably visually see that x in this case would equal 1. Any questions on that calculation there? At this point, we have now figured out the orders for both F2 and ClO2. We could actually write our completed rate law. Our completed rate law would be the rate is equal to K times F2 times ClO2. And much like everything else in chemistry, it's implied that it is a 1 and 1 on top. You don't have to put it here. The overall order at this point would equal 1 plus 1, which would be second order. And again, that comes from adding the 1 and the 1 together, the orders of each of those guys. Now, the last thing that we could do once we figured out the order, so we got that guy done, we got that guy done, is we can now figure out the actual value of the rate constant, which is K. So I could take my rate law and rearrange it and solve for K. K would equal the rate divided by F2 and ClO2. Now you may ask yourself, where can I get that information from? The answer is you could go to this table and you could choose any one you like. You could choose entry 1, you could choose entry 2, you could choose entry 3 and use the numbers, and they all should come out the same because it's a rate constant. I'm just going to choose entry number 1, and that means I'm just going to put those numbers in. Gives me 1.2 times 10 to the minus 3 molar seconds divided by the concentration of F2 in the first one, 0.1 molar, times the concentration of ClO2 in the first one, 0.01 molar. That gives me, when I divide it out, 1.2 to the minus 3 divided by 0.1 divided by 0.01 gives me a 1.2. Now, when we do the rate constant, the units are important because it tells you a lot of pieces of information. In terms of what is canceling out, molarity up on top will cancel with one of the molarities on the bottom, which will leave you 1 over molar seconds, or if you want, 1.2 molar minus 1 seconds minus 1. That's the way you can do it there. And those units that we see here of 1 over molar seconds are the typical units for the rate constant for a second order reaction. So you want to make sure that you write the units there because it really is important. Question on any part of that calculation. This is again a typical problem, kinetics problem, where you're given a table where you find basically, all those 3 pieces of information based on what's there. Any questions on that there? Okay, so we'll lay it up there for today in terms of lecture. Let's see. Thursday we are taking an exam, so we'll do it during lab time. So we'll do a little bit of lecturing so we can get through a little bit more of this kinetics chapter, I think. And we'll break and we'll do the experiment, and we'll do the exam there on Thursday.